Hey everybody, welcome back. So in this video we're going to look at a new phenomenon where the photon model of light is successful in explaining what people observed and the wave model was not successful. So this is known as Compton scattering, which is the scattering of X-rays off of electrons. And the way you typically observe this, and the way it was observed historically, is you take some X-rays of some wavelength and send the X-rays through a thin sheet of metal foil, and you observe which ways the X-rays end up going, which way they scatter. And the observations that people saw, they couldn't really explain using the wave model of electromagnetic radiation, but the photon model was successful. Some history. So X-rays are called X-rays because people really didn't know what they were. They discovered them by accident, and you may have read about this. Some guy named Röntgen, R-O-E-N-T-G-E-N, he was playing around with cathode rays, which are beams of electrons. And in those days, the only way they could detect where the electrons or cathode rays went, because when cathode rays were first discovered, people didn't even know that they were streams of electrons. But the way they detected where the cathode rays went is they would use those old glass photographic plates you may have seen in movies, period piece movies, where they use those old box cameras, like in old westerns and things. They have to slide these big glass plates into the back of the camera. So those glass plates had a emulsion layer coated on them. And when light hit that emulsion layer, you would expose the emulsion, you get a chemical reaction. And then you would have to develop the plates, put them into a developer chemical, and then you'd get another reaction from the exposed emulsion, and you could produce the negative, so-called negative of the photograph. Well, to see where cathode rays went, people were using these big glass plates with the emulsion. So the cathode rays, right, would hit different areas on the glass plates, and people wouldn't know where they hit until they did the development. But the cathode rays would be doing the exposing. So the story goes that he had a bunch of these emulsion plates sitting in his lab, and he was using cathode rays and had some sort of stop, like big sheets of metal to stop the cathode rays. And it turns out that I guess he had some plates, these emulsion plates, near that piece of metal. And so when he went to develop them after using them for an experiment, all of these plates were already exposed. They were just completely overexposed. So he was able to figure out that some type of radiation was coming from that metal stop exposing these metal plates. So then he started looking into this radiation and called it X-rays, and started to look at characteristics of these X-rays. Now we now know that this is high frequency electromagnetic radiation, but at the time Röntgen didn't know that. And then he discovered that these X-rays could penetrate things really well, like people. So people were getting their X-ray photographs taken. I think the story goes the first official X-ray image was his wife's hand, and people didn't realize that maybe there was a little bit of danger or a lot of danger, depending on how much X-ray exposure people were getting. But anyway, so once the X-rays were discovered, people started using them for experiments. So as I said, what you can do is you can send these X-rays through a foil and observe where the scattered X-rays go. Okay? Now, in that picture there, and I'm not sure how good the resolution is, I'll sketch it again in just a minute, but you have an X-ray coming in from the left, and this formula, I'll describe how you get this formula. This is known as the Compton shift formula. But the relevant parameters here, the wavelength of the incoming X-ray, we're going to call lambda naught. So just consider one wavelength of X-ray coming in. And when it scatters through this foil, the scattered X-ray will go in a certain direction relative to the incoming axis, at angle theta. So that's called the scattering angle. So that's the angle that the scattered X-ray goes measured from the incident direction. Okay? All right. Now, when people did this experiment, they didn't know that there was this electron flying out of the metal. This is going to be important when we do the photon model explanation. All they knew is that the X-ray would be scattered. Okay? They also could measure that the wavelength of the radiation, because they could look at how the X-rays diffract, so they could determine the wavelength of the X-rays. That the scattered X-ray had a longer wavelength when it's scattered. Okay? Now, it turns out that there is a relationship, and that's lambda prime. So lambda prime is the wavelength of the scattered X-ray, which is longer than the wavelength of the incident X-ray. And this X-ray, again, is scattered at the scattering angle theta. Well, people discovered that there's a relationship between the angle and the two wavelengths. So the scattered wavelength and the scattered angle, there's a relationship with those quantities with the incident X-ray. Well, I guess what I should say is there's that shift. So the difference between the scattered X-ray wavelength and the incident X-ray wavelength, you can relate directly to the scattering angle. That's a better way to say it. And that's what you see written here. This is the shift, right? The difference in the wavelengths. So that shift depends on the scattering angle. Okay? But what's interesting is that what it doesn't depend on, and that's where the wave model fails. First of all, the wave model cannot get this formula. It doesn't predict this exact dependence. But also, it seems like in the wave model that there should be some dependence on the intensity of the X-ray electromagnetic radiation. So if you crank up, right, the intensity, that should affect the scattering, but it does not. The other thing that's interesting is that there's no dependence on the actual scattering metal. Okay, so this relationship, as you see written, doesn't depend on anything that's characteristic of the type of metal. And again, we'll derive this in just a sec. Well, we won't officially derive it. I'll describe the derivation. But you can see in the formula that H is Planck's constant, m naught is the rest mass of the electron, which is what we think of as the regular mass in physics 2, for instance, okay? And then the speed of light, c. So there's no dependence on the actual type of atom that is doing the scattering in this metal. So very, very unusual, right? That's not, that should not be, or you would not guess that based on the wave model of light. But the photon model explains it. So let's see how the photon model explains it. And I'm going to go to my notebook here so I can sketch this. So what you have is in the photon model, oops, there we go. You have this incoming photon with wavelength lambda naught. And, you know, here's this metal right here, this metal foil. But what you do, the way you figure out what's happening is you view this as a collision event. You treat the photon as a particle that carries momentum, and you treat this as a collision. Now, in the collision, what happens, and this is my reference axis, that's the initial direction, is it's a collision with an electron on one of the atoms. So what happens is you're going to get an ejected electron. So here comes this ejected electron, E minus, right? And it's going to come out at some angle. I'm going to call this angle phi. And then you have the scattered photon. So here's the scattered X-ray photon right here with wavelength lambda prime. And it's going to be scattered, if I continue that line, it's going to be scattered at some scattering angle theta. Again, when people did this experiment, you know, you don't see this electron. You can't catch that, but you can see the scattered X-ray photon. Okay, so what you do is you say, all right, to analyze this, actually the analysis is fairly simple. It doesn't require anything beyond some basic physics, although you do have to use relativistic mechanics, and I'll mention that in just a second. But in a collision, right, we know that momentum is going to be conserved as long as we look right before, right after the collision. Now, this is a two-dimensional collision. Okay, so let's call the horizontal direction x. So if I go to conserve momentum in the x direction, I have coming in the incident x-ray. Now, if you remember, one way you can write the momentum of a photon is Planck's constant over its wavelength. So in the x direction, I have all the momentum of the incoming photon. So that's h over lambda naught. Now that has to equal the sum of the x components of the electron momentum and the scattered x-ray photon momentum. So here's the scattered x-ray. It has a momentum magnitude of h over lambda prime, but the x component is going to be that magnitude times the cosine of the scattering angle, theta. Okay, then I have the momentum of the electron x component. So I'm going to write that as p sub e cosine of the angle phi. And those are both positive x components, so I add them up because they're both going to be pointing to the right. Okay, so there is one equation. So this is equation 1. Okay. Then we have, if we conserve momentum in the y direction, now the way I set this up, right, I'm saying that the incoming photon is only traveling in the x direction, so there's no momentum in the y direction. So if I take the upward momentum component, y component of the electron, that's going to have to balance the negative y component of the photon. Okay, so I'll write this as, I know this is going to be a negative component for the photon, so the magnitude of the momentum is h over lambda prime, but I need the y component, so I have multiply that by the sine of theta, and then I have the positive p sub e component in the y direction. So p sub e times sine of phi. So there's number 2. Now, the other thing that I can invoke is conservation of energy. And this I'm going to model as an elastic collision. So coming into the collision, I have the momentum of the energy of the incoming photon. So I'm going to write that as hc over lambda naught. Remember, energy of a photon is hf, frequency, or I can write it as hc over wavelength. So that energy is what comes into the collision. What leaves is the scattered energy, the scattered photon energy, hc over lambda prime, plus the kinetic energy, big K, of the outgoing electron. So this is equation 3. Okay? Now, here's, though, where it gets a little bit more complicated. The electron is going to be traveling so fast in this very energetic collision that you have to use what we call the relativistic expressions for momentum and kinetic energy. So you have to use the special theory of relativity. We're going to talk about that in part 4 of the course. We'll look at the relativistic expressions. So when particles with mass are going fast enough, you have to use these relativistic expressions. So for instance, we're used to momentum, right, for a particle being the mass times the velocity. But if that particle is traveling fast enough, and typically this is going to be maybe like 10 to the 7 meters per second. That's pretty darn fast. Speed of light, right, in vacuum is 3 times 10 to the 8. So you're moving around 10 to the 7 or faster. This doesn't cut it anymore. What you have to use, and I know it looks like I'm pulling this out of thin air, but we'll talk about this again in part 4, is there's a factor, 1 over radical 1 minus v squared over c squared. That's all underneath the radical. So this is my factor. We'll call this the gamma factor. times m naught v. Now, m naught is known as the rest mass of the electron, which is what we normally think of when we say mass of the electron in regular old physics, 9.11 times 10 to the minus 31 kilograms. Energy, kinetic energy. You cannot use 1/2 mv squared when v is getting near the speed of light. In fact, what you need to use is the relativistic expression, which is, in parentheses, this gamma factor, 1 over radical 1 minus v squared over c squared. Okay. Oops, sorry. I don't want. Let me see if I can. Yep. I forgot to subtract. This is minus 1. Close parentheses. Then we have m naught and c squared. Okay? I know that looks really strange. And I assure you, if v is a lot less than c, which is what we think of as our normal objects, right? These expressions, these relativistic expressions right here, they do revert to mv and 1/2 mv squared. I know it may not look like, well, this one you can sort of see. The momentum one, if v is a lot less than c, that v squared over c squared is much less than 1, so that whole thing in parentheses is basically 1, and you're back to m naught v, right? It's a little bit harder to see how, if v is a lot less than c, in the kinetic energy expression, how you get 1/2 mv squared. 2 words for you, Taylor series. Yep. I'll mention that when part 4. If you do a Taylor series expansion on that 1 over radical term, you can actually get 1/2 mv squared. Okay, so here's what you have to do. If you look at those 3 equations, which I've numbered 1, 2, and 3, okay, if you notice, there are really 3 unknowns. Okay, and the 3 unknowns, what are our 3 unknowns for this experiment? Well, we want to know what the scattering angle is, right? Because we want to get an equation for the scattering angle. That's one. But we don't know what the speed is of the ejected electron. Okay, so we don't know what that is. And we also don't know what the scattering angle phi is for the electron. But we have 3 equations. So we should be able to actually solve this. Okay, the knowns are the 2 wavelengths, lambda naught and lambda prime. So we can't actually get a formula involving just one unknown, the scattering angle theta. It's a little bit messy algebraically. You can imagine eliminating v, right? Okay, it's a little bit messy algebraically. But I promise you, if you do that, you will get this equation right here. And this is known as the Compton shift equation. So lambda prime minus lambda naught, that's the Compton shift, is this collection of constants, h over m naught c. And you can see where these come from, right? If we go back to the notebook, you can see where the h and the m naught and the c are coming from, okay? They're coming from photon momentum and the relativistic expressions, okay, for momentum and kinetic energy. So that shift is h over m naught c times, in parentheses, 1 minus cosine theta. So the photon model, boom, drops right in your lap that this shift in wavelength, its dependence on the angle theta, it's right there. You can check that with observation. It works. And you can see that there is no dependence on the actual type of atom, right? This scattering angle theta, right, determines the shift. So lambda prime minus lambda naught is going to give you a certain theta no matter what type of metal foil you're using. It's a really cool result and a big triumph for the photon model, okay? This collection of constants right here, h over m naught c, that does have units of length. So that's known as the Compton wavelength. Sometimes it's abbreviated lambda c. And it turns out to be 0.00243 nanometers. So these shifts are extremely small. The wavelengths themselves are very small because these are high frequency photons. Okay, but there it is. one thing that's, well, a couple things, I guess. If you look at this formula, notice that if theta is 0, then I get 1 minus 1, right? There is no shift. Well, that makes sense. What that means is there was no scattering event. There was no interaction of the incident X-ray with an electron, so it just shoots straight through. Okay? Also notice, for all angles theta, right? This cosine theta, the biggest it can be, right, positive-wise is 1, and the smallest it can be negative-wise is -1, right? But you're always going to get a longer wavelength, scattered wavelength, than incident wavelength. They would equal if there's no interaction at all. But this makes sense because when the photon collides with the electron, it's going to lose energy. Some energy goes into the kinetic energy of the electron. So the scattered X-ray photon should always have less energy than the incident photon. Well, less energy means longer wavelength. So you always should get a scattered wavelength that is longer than the incident wavelength. And if you notice, the biggest shift, the biggest energy loss will be when cosine theta is -1, because then this number in parentheses would be 2. That's the biggest it can be. The shift there would be 2 Compton wavelengths. Well, when does cosine theta equal -1? Well, when theta is 180 degrees. That is when the scattered X-ray goes right back in the same direction, right to the left of the incident X-ray. That makes sense in terms of collisions, right? In a conventional collision, you have something coming in and hitting something. When it goes straight back, that's when it's going to lose the most energy. We call that backscattered, completely backscattered. Okay, so this is consistent with collisions, and it works. All right, so you should know what we mean by Compton scattering. You should know that the photon model explains it, and you should also just know this equation, know what these things are, and be able to use it. Okay? All right, that's it. Bye-bye.